Good evening, everyone. My name is Riccardo Freschi. I am a solution architect at AWS. My job is, on a day-to-day basis, to work with partners and customers and basically help them in their journey or projects, anything to do with the cloud. And my focus is on modernization and specifically on containers. So as part of my job and the job of the other SAs, solution architects at AWS, we focus on, of course, different domains, and we work a lot on AI. So I thought today of showing you, describing a pattern, so a architectural pattern that we, one of those that we open sourced as Terraform modules on GitHub, which is exactly to address one aspect of AI. So in this case, we have many, and this one is to deploy inference, so inference workloads, which run on Triton specifically, NVIDIA Triton server. The specific workload that I am going to show, I will mention that, well, occasionally is LLM, an LLM. But it's not really relevant for this talk and specifically this pattern, because it can be the model itself and the different workspaces can change independently, can be interchangeably switched within Triton, and it doesn't change much the deployment. Okay, so before diving into maybe the details, I thought to share some of the areas and the subjects I've seen recently while working on some AI topics that myself and other colleagues have worked on. Because we talk about AI a lot, but maybe from a business perspective and from use cases perspective, it might be interesting for you to hear from a cloud provider what are things that people do with AI today. So, like you know, there are different levels of the stack at which we can operate when we talk about AI. And going from managed services, like we and other cloud providers have, so operating at the top level of the stack, where everything is managed, and the people, users, just need to maybe call a endpoint and just receive some reply. But today, because we are looking at this pattern, which is at a lower level, so it uses Kubernetes, it uses containers, we are talking about deploying workloads, then I'm going to share a little bit of a view on what people are doing at this level of the stack. So we see a lot of customers and partners working in a financial services area that are using these approaches. So they are looking at deploying Kubernetes, machine learning, AI in general, workloads on Kubernetes. And they are looking at things like, for example, building stock advisors based on their own data. They are looking at, for example, auction companies. They are looking at trying to predict the prices for goods that are going on auction. They are looking at observability issues, so they want to know what is running in their clusters and how the performance, because cost is very important. So they are trying to reduce their costs. Of course, we all know that the GPU instances are quite scarce, and they are not cheap. We also see a lot of medical companies where they try to infer, so image scanning. They do image scanning. We also see a lot of companies still in medical, but they are trying to, for example, create some assistance. So this is a similar activity that they do, that other companies do within within help desks, where they try to support callers, so people who are trying to get help. And when they need to scale, that's one of the issues. So they are trying to address scaling issues on their clusters. We also see a lot of companies doing video processing and trying to include the video AI models within video processing as well. Okay, so these are a few trends that I thought to share with you before starting with this pattern, so this design pattern illustration. So the objective, like I said, is to show you how and this is one of the patterns which we publish, how to run, deploy and run with observability workloads that are running on Kubernetes and specifically on Triton. Okay, so you can see the first of all, I will actually zoom in and out because I put everything in one infographics. I will go up and down. Maybe it's easier for me to, and hopefully easier for you also to maybe visualize a little bit the focus here and there. So let's start with the cluster itself. So you can see this this area here, which is showing you the cluster. The control plane is outside. This is just basically the data plane. The control plane in our open source pattern on Terraform is, of course, Amazon EKS, which is our Kubernetes managed version, which is fully compatible with Kubernetes. So you could take this pattern and deploy on your VMs or machines in general, and just apply changes to actually maybe change the interfaces to the cloud provider, so AWS. But anyway, all of this is fully compatible with Kubernetes, and with some tweaks you can make it work with other solutions. So starting from the left, you can see that we have a big, large area which I named the regular instance. This is a group of instances which are managed node groups. So when we started the cluster, that is the first group of instances which is created. It's set to 2. You can, of course, scale it out and set it to a different number, but it doesn't matter. So it depends on your workload. The thing is that in here we host the critical add-ons, which are shown at the bottom there. So you can see the CSI driver, core DNS, and others. The one that I'm going to explain to you right now is the Carpenter add-on. I am assuming some of you are familiar with it, but in any case, I'll explain how it works and what that is. So Carpenter is an open-sourced autoscaler. It's an alternative to the cluster autoscaler. The way it works is that it looks at pods that are pending and requests additional instances to the cloud interface, let's say. So I'm going to show you a little bit how this is done a little bit more in detail. So the objects which Carpenter uses most are the node class and the node pool. The node class is a object that encapsulates information like the machine image and subnet security groups and other specific properties of the node that we want to create. The node pool is the is another object which includes the options that we want to request our cloud provider to produce. The options meaning from a list of instance families and sizes. So, for example, we want to request GPU instances, and we want to request GPU instances smalls or larger. We put all this information into one, let's say, big bucket. So the node pool represents the types of instances, the types of VMs, to speak in a more general language, or EC2s in terms of in AWS terminology. So these are the types that we want Carpenter to pick from when calculating what instances we need. I'm saying calculating because Carpenter, by looking at our current capacity, so the data plane, how it is built, and all the instances that are running, and or the pods that are running on top of them, Carpenter makes a calculation depending, first of all, when we add pods and they are on pending, because, for example, there is no capacity left. So it makes a calculation to compute based on what we tell it, to choose the right instance type and size to actually fit the additional pods. It also has another feature which is interesting, and it is that it also is able to disrupt the current recurrent node in the data plane because it looks at possible improvements that we can make. So, for example, if we have two nodes running with one pod each, and these pods are not actually filling, they are actually maybe only filling 10% of the node capacity, it makes a calculation and removes one node and puts the one pod into the other node. It can also actually make another calculation, judge that actually that node that is running, that now that we have removed the other one, is even too large, and therefore it removes this node and replaces that with a better fitting node. So from a cost optimization perspective, this autoscaler Carpenter is a good fit, and this is how it works. So this is a snippet that shows in the pattern that we are using, the design pattern, what we are setting. So in this case, you can see that we are using a G5, which is a GPU instance, and we tell down below where you see instance size, we tell Carpenter that it can choose between all these sizes. On the top part of the snippet, you can see that we are adding labels and taints. So the labels are for the pods to be able to select the nodes that they want. For example, we will see later the Triton pods will want to land on these kind of nodes, as opposed, for example, to the others that are on the base core autoscaling group. We also have taints because we don't want other types of workloads to land on GPUs while they may not need the GPU capacity. So let me show you a little bit in here how Carpenter works when adding a node. And by the way, the description that we've just seen applies to the group of nodes which is not on the base managed node groups. It applies to the additional workloads that we want to run for the AI, which is shown. Well, let me go back. Which is shown here. It is basically this one. We will talk about it in a second. So, this area here is the is representing the managed node groups that host the critical workload, the critical add-ons. While here, Carpenter creates these additional nodes hosting those workloads. In this case, it's Triton, with the snippet, with the basically node class and node pool that we defined in here. So I was saying about the how Carpenter works when adding nodes. So a node, it first creates a node claim. A node claim is like a declaration of what will be created, what kind of node will be created. And then it requests the instance to the cloud provider, AWS, but it can be others. Carpenter is also supported, and the interface is implemented in other cloud providers, by the way. And then when it is launched by the cloud provider, the instance then registers with the cluster, and then finally the node is labeled as ready. You can see on the left all the states that this VM can go through, which is reflected in the node claim. So the node claim actually goes through these states, and you will see that updating during this process. So let's go back here, and let's have a look now at this area here, where we have the GPU instances. So when you first launch the cluster, if there are no Triton instances launched, that square rectangle doesn't exist. So it only exists when you launch a new workload that requires some conditions, and we will see. But there is no capacity. So Carpenter will see that it is pending and will be creating these nodes. So Triton. I'm not sure how many of you are familiar with Triton, but it is also an open source component. It is an inference server. So it helps, it runs models and allows you to make requests to Triton and receive replies. It can host and run multiple models in parallel, and also with different frameworks, supported by different frameworks. For example, I don't know, on Onyx, TensorRT, VLLM. VLLM is the one that it is used in this example. And the way it works is a little bit this. When it comes to, because I said that it actually runs multiple models, in terms of concurrent model execution, Triton works this way. So for every model, there is a model backend. So backend represents an engine that is running the model. Like I said, for example, VLLM and TensorRT. It supports many others, by the way. So for each one of these backends, there is a queue where the inference requests come in. They go through a scheduler which is associated to the backend, and the backend can, depending on our configuration, can have multiple instances of the model running. So you can have the same model running in parallel within Triton even, well, depending on a configuration that we will see in a minute. And in order to execute parallelly these models and to optimize the GPU utilization, Triton leverages the CUDA streams. So what it does is basically it takes the instructions, let's say, from these requests from these model instances and maps them from the execution context, which is generally mapped one-to-one to the model instance, and translates that, takes any amount of CUDA stream and multiplexes them and pass it on to the hardware scheduler. So you can see that basically if a model is not running or is running low and another one is running faster, or because it is more stressed, you can have these requests for execution pipelined into a single scheduler, which is the hardware scheduler, which can make better use of the CPU. There are other options which for concurrent scheduling, which are not used by Triton, but if you don't use the Triton inference server with NVIDIA GPUs, you can also see that you can leverage other concurrency mechanisms that are mentioned down below. So the time slicing, which is a little bit similar to what a scheduler on a CPU does. So it basically breaks down the time into multiple slots and assigns these slots to different threads or processes. In this case, it is just the time that the GPU is assigned to different model executions or in general workloads. You also can have multiple instance GPUs. In this case, instead of time, the GPU is divided into space. So it is broken down into some areas within the GPU itself, and this has the advantage that the fault isolation is higher. So because every slice of the GPU now works independently. So if there is any problem with one workload, it is not affecting the others. The downside is that there is a maximum number of these partitions that you can create, and not all especially the old GPUs, they don't allow you to do that. Time slicing is a better fit when you need to have multiple of these workloads running. But the fault isolation is limited. So this is, in a nutshell, what Triton does and how it does it. So let's have a look a little bit of how a model repository looks like. So when you want to launch models on Triton, like I said, you can have multiple models running. The typical model repository is shown here. So what you do is you create let's say a single repository, which can be local, for example, if you're running on your local machine, or it can be externally hosted, like you see in here. I'm referencing a external persistence in AWS, which is S3. So like I was saying that you have a folder structure which looks like that. So you have one folder per model, and as a subfolder you have the version of the model. This is because also the different endpoints of Triton, which could be of type HTTP or well, HTTPS. Each model is mapped to one, and version is mapped to one of these endpoints. because, like I said, it can serve multiple, run and serve multiple models at the same time. Within the version, you see the model. So the model itself, in our case, which is a VLLM backend, the model is not completely hosted in there. There is a script, a Python script, that will load the model from the Hugging Face repository. The config file that you see there is the one which I will be showing to you in a minute, and is used to actually control a little bit the behavior of Triton. I will show you a little bit of parameters that you can tweak. There are many, but in relation to this pattern, I'll show you just the ones which are relevant. So I was saying that, so Triton this is the Triton pod, and which is, like I said, is pulling the model from Hugging Face. And in order to actually be able to pull the model, the secret, the key is hosted into a secret object, which is then accessed and used to access the repository of the model itself. Down here, you can see the device plugin, NVIDIA device plugin, which is basically responsible for surfacing between the many things, it makes the GPUs accessible to Kubernetes workloads. So let's have a look just a second about the configuration of Triton. So first of all, in the deployment of the Triton pods, you can see in the repository, you can tweak the number of GPUs that the Triton accesses. So already in here there is a level of let's say multiple levels where you can operate. One of these in relation to running multiple concurrency, in relation to concurrency of inference. So for example, in here we are, let's say that the GPU has, the instance has 4 GPUs, which is the default on the Terraform module. With that definition, with that snippet there, we are actually selecting Triton to access the full 4 GPUs. This is good because Triton can actually handle multiple GPUs and can map the different inference requests in the way that we've seen before. So schedule the different inferences on the different GPUs, because it can actually manage them. So when it comes to the configuration, what you use is the config file, pbtext, that you've seen before in the model repository. And in here, for example, we can this is again a snippet taken from the repo. You can see there count 1 for, so this is related to one model, a version of a model. So you can ask Triton this way to execute multiple instances of that model. For example, the first part up there requests to have one instance of GPU type on GPU number 0. While you can ask, and you can also therefore map the model instance to the exact GPU. Same thing you can do on the same model. You can request to have additional 2 model instances running now on GPU number 1 and number 2. There is also another parameter. I'm just going quickly through this. It is not used in the pattern, but in any case, you can enable dynamic batching with Triton, which is a way to group requests together so that you achieve higher efficiency. So you group them together, and you allow Triton to request to group the requests together and to pass them on to the models. You can have preferred batch sizes, so batches can vary, of course, and you can set, for example, like in there, I want batches of requests of 4 and 8. And you can also set a queue delay, maximum queue delay in microseconds, because, for example, you wanted to tell Triton to wait for a maximum amount of time before sending over the requests for inference. Okay, so now we discussed Carpenter as an autoscaler. Carpenter as an autoscaler operates on our capacity, but first, before expanding the capacity, we needed to have a reason, which is our pods, our workload need to scale out, and which is the first thing that happens before the scaling of the capacity. The scaling capacity, again, the need for scaling the capacity is detected by Carpenter because there are pods in pending state. So before that happens, we need to scale the pods. So the scaling the pods happens through the horizontal pod autoscaler. Now, in this specific pattern, we are using the Prometheus stack, which deploys Prometheus, Grafana, and other stuff together with the Prometheus adapter. So the Prometheus adapter, what it does is, first of all, we have Triton, which is exposing a number of metrics. One of these metrics, and this is the one we use in the pattern, but you can choose others. They are all documented, of course. First of all, this is the time that the requests spend on the queue. So the queue, if you remember, is here. It's by model. It's by model and backend. So this represents the inference time that is spent by requests on queue. So this is a good parameter to pick when we want to scale out, because reasonably, if we have a large number of requests queued before the inference, it means that there is some kind of bottleneck, spike, whatever. So, and this is actually the metric that is picked up by the Prometheus adapter, which registers the custom metric with the API aggregator, which is used by HPA, the horizontal pod autoscaler. The actual manipulation of this metric is actually shown down below. It is basically a transformation to first of all into a rate, and then it is you don't see it, just a second. It is scaled to milliseconds instead of microseconds. Not much of a change, but it basically it explains that it is reflected into the horizontal pod autoscaler, which is looking at these metrics and deciding how many replicas it needs to run. If you look at the repo, you will see that the replicas are set between 1 and 5. Of course, that can be changed and tailored to your needs. Okay, so this is a little bit the full explanation of the how the pattern works. I just wanted to maybe share a couple of, let's say, additional tweaks that we suggest to customer and partners when they approach and they see problems with booting time, basically cold starts. So, like I mentioned, some cases, use cases that we've seen, have highlighted that customers want to are concerned about the time it takes to actually boot up instances, to actually scale out. And this is related to the fact that first we needed to, when we need to scale out, first we needed to detect that there are pods pending, then we needed to increase the number of instances, and this is done by Carpenter. And then we need, once the pod is scheduled to land on an instance, it needs to launch. So the container needs to start, run, and once it's running, it needs to download the model, because you've seen, for example, in there it's hosted somewhere else, okay, in a persistent storage. That's the this here. So first of all, this is for hosting the models, which can in turn not only mean that you need to download this repository, but if then the model is referencing another model on another repository elsewhere, it needs to access that as well. But in any case, generally the models are quite large, and also the containers can be quite large, and therefore the time it takes for the process is actually quite long. Especially, we've seen especially the downloading, the pooling of the image and the pooling of the models. Models, because of can range in gigabytes, tens of gigabytes to hundreds. They can take a long time. So some of the improvements that we have been looking into are listed in here. So first of all, the SOCI, so seekable OCI. These are addressing the problem of having to download a full container while maybe you need just a portion of it in order to start the workload. So this is by the way, it's again an open source project which is built on a separate index artifact. So you run your image through a tool which creates an index and basically shows which are the components, the layers of the container that are essential for starting up, and we'll download those first. We'll run the container, will start up the container, and then the rest of the layers will be downloaded later. This process is done by the snapshotter, which is by default for containerd is overlayFS, like you know. But the SOCI snapshotter is the one that implements this logic that I just mentioned. You can also use multi-stage builds. Basically, you change your image in your Docker file, starting maybe from a larger one because it includes multiple tools that you needed to build the container, and then you switch to within the same file, you change the from, and so you change to a smaller image so that you will be able to create an image that just needs the bare minimum. So another option, and this might be the one that leads to faster results, is using the Bottle Rocket operating system. This is another open source project which is an operating system, and it tries to basically provide a Linux distribution which is minimal, so it reduces the footprint and the attack surface. And it is also designed so that it has two, for example, volumes, an OS volume and a data volume. Why is this useful in this case? It is useful because you can, for example, run an instance with Bottle Rocket, pull the Triton image with the models into the data volume. They are separate, okay? Then you can take a snapshot of that data volume. Our snapshots go into S3, but I'm sure there is a similar procedure for other solutions. And then when you need to launch a cluster, to create a cluster, that is done offline, by the way. It's not part of your deployment up to here. And then when you need to create your cluster, what will happen through this configuration, for example, through the node class that Carpenter would use, will, by selecting the snapshot ID in here, it will take the snapshot that you created and is now hosted in this persistence S3. So what will happen is that at launch, your node will include already the image and the model. So there will not need to be a pool of a separate model and a container. Okay, so I think I have shown you everything that I wanted to. Now let me maybe just show you, I have a few minutes, just as a small example of what I mentioned before in relation to the autoscaling based on the metric. So the horizontal pod autoscaler, which creates multiple replicas, which you can see in here on the right. You can see 3 spikes here that are correlated to these spikes also that are related to requests, to a large volume of requests that are coming to Triton Inference server, and therefore the queue becomes much larger. This is a logarithmic scale, and this is the 10 millisecond boundary that is set within the pattern. And when you see that there are spikes going beyond that line, that's where these scaling events happen. This is again the scaling of the workloads on HPA. 1, 2, and 3. These are lower spikes, but are not considered enough for the scale out of the workload. Maybe very quickly, this is just a snippet of what happens. This is related to the events within Carpenter. So this is from the first Triton pod that is launched. You can see that there is a container creating here. We can see the nodes in here, which are just created here. You see 3 minutes, while the other 2, which were in the main base autoscaling group have a longer life. This is launched to support this one. Now it's running, and then when there is a spike in the queue length, you can see that there are up to 5 now pods, Triton pods created, with our original one running for 15 minutes, and these ones just created. Again, so to support these pods, then a Carpenter kicks in, nodes here, and then the flow goes on with the container creating, because now the pods are placed and scheduled on the related nodes, and then they are in running state. I think that's more or less it, what I wanted to show. And thank you for listening.
How do you handle smaller use cases? I mean, sometimes you don't need like a whole GPU for a model because it is small, like, I don't know, Mixtral 7B or something like that. I know there are solutions on open source solutions that allow dividing the GPU into parts. Like you can assign, I don't know, a fraction like 10% of the GPU to the model. Does Triton support something like that?
No. Well, first of all, Triton is NVIDIA Triton, so they built it and open sourced it. It's not our product. Yeah. So Triton uses this approach, which is basically the multiplexing. So instead of you having to divide the GPU into multiple chunks, Triton uses the CUDA streams. So it looks at everything that it has to do in terms of operations that require GPU. Operations can be of different types and are related to the different model instances. So if there is a request related to a model instance and then another request for another model instance, and again and again and again, it looks at all of them and basically multiplexes them and hands them over to the GPU so that the hardware scheduler can take all of them and run. The other option that you mentioned is probably the time slicing and multi-instance GPU. The multi-instance is the one that you just mentioned, which is the one spacing, dividing the GPU in space, so breaking down into multiple areas.
When I believe this is more operating on the hardware level of the NVIDIA solution. And the thing I was speaking about is operating more on the software level. Like, for example, in Kubernetes, you can assign like a 0.1 CPU to the pod. And with these solutions, you can assign something like that, but with GPU. So you can assign like a, I don't know, 0.3 GPU per pod. So I was wondering if Triton supports something like that, simply. On the software level, not the hardware one.
As far as I know, it doesn't, because it doesn't use that approach.
I haven't used the Triton itself, but the question is, how many models can you use with Triton? Let's say I have 50 models, and I'd like to run maximum 4 at the same time. Can the Triton dynamically change the models depending on the incoming requests?
So you mean, so you defined the models, if you remember, here. Okay, so Triton by default loads all of them. I think there might be a parameter which you can set and tell Triton, I just want you to load these models, but I'm not sure.
Yeah, because right now we have a problem like we have something like 50 models, and we know that we are going to use maximum 4 to saturate this GPU capacity, and then we would like to be able to that there's a new incoming request, then unload the least used model and then use the new one.
Kind of swap them.
Yeah.
Yeah. So in order to be able to optimize the usage.
So my question is, this Triton server is running as a pod on a GPU-powered instance. It's just standard EC2 instance, or it's some dedicated hardware? What is this?
So the instances within AWS
Yes.
are of different type and size.
Okay.
The GPU instance is a part of a still EC2, Amazon EC2 instances, but it includes GPUs, so the NVIDIA GPUs.
Okay, and then my question would be, so in your pattern, let's say, yes. By the way, can you share the link to the GitHub with this repo?
Yeah.
Yes, I want to see it. Are we able to, because these GPU instances probably, I don't know prices, but are quite expensive, right? Can we scale out this to 0 if we not use it or not?
Yeah, like I said, when you launch it, if there is no workload,
then
Carpenter removes it.
Removes it completely. And
Yeah.
No Trident server is running, so we are like 0 GPU.
Yeah.
Okay, makes sense.
Okay.
Thank you very much.
Thank you.